This lesson will cover quadratic linear systems. The learning goal is to understand the purpose of the discriminant and to locate the points of intersection between a linear function and a quadratic function. The success criteria is you can determine if a quadratic and linear system has points of intersection using the discriminant, and you can algebraically determine the points of intersection in a quadratic and linear system. A system of equations is where you are working with two or more equations at the same time. Now, the solution to a system of equation is the point of intersection. A quadratic linear system can result in three different scenarios based on the position of the linear function and the direction of opening of the quadratic function. So these three situations or scenarios are here. There can be a case where a quadratic function and a linear function don't even encounter each other. The quadratic function can, for instance, be opening up, and the linear function has a negative slope and is below the vertex of the quadratic function. That has no solutions. There's no point of intersection. There can be a single point of intersection where a linear function just touches the vertex of the quadratic function, or might touch a point, might have like a tangent touch, might touch a single point on the curve. We can say that's one solution. And then finally, you can have two solutions where the linear function and the quadratic function do cross each other twice. In this case, the linear function has a positive slope. It crosses the parabola here, and then further up along the way, it has another intersection. So that's two solutions. Now, graphically is very easy to tell, but we can also check algebraically. So, for the first example, we're going to determine the point of intersections, if any, of f of x equals 2x squared minus x minus 1, and g of x equals 3x plus 5. So to look for points of intersection, you need to set your equations equal to each other. So we're going to take f of x equal to g of x. And that's going to give us 2x squared minus x minus 1 equal to 3x plus 5. And then we're going to solve for x. So that's going to give us 2x squared. We're going to subtract the 3x and 5 to both sides. So it's minus 4x minus 6 equals 0. And then by the looks of this, we can do a quick factor. So that's 2, and then x squared minus 2x minus 3. And it's a simple trinomial, so that gives us 2, x minus 3, x plus 1. 0, x is equal to 3, and x is equal to negative 1. So therefore, there are 2 points of intersection at x equals 3 and x equals negative 1. However, it may not be always that nice and clean as we look at the next example here. An asteroid is moving in an arc that is modeled by the function y equals negative 6x squared minus 370x plus 100,900. At the same time, two space probes are moving along different paths on the same plane. The first probe is following a path defined by the function y equals 500x minus 83,024. The second probe is following a path defined by the function y equals 500x plus 133,705. Determine where, if at all, each probe collides with the asteroid. Let's actually get a little bit more space in here. So we have one quadratic function and two linear functions. We have to do each one separately at different times or in different instances. So let's do the first probe first. So we're going to set negative 6x squared minus 370x plus 100,900 equal to 500x minus 83,024. And then we need to move everything over to one side. So that's going to give us negative 6x squared minus 870x plus 183,000. Whoops. 83,924 equals 0. Equal sign's not exactly lined up there, but that's all right. All right, so we have our quadratic function right here. It looks like a major pain to factor normally. So let's do quadratic formula. So we have A, B, and C. We have negative b, which is 870, so we have 870 plus or minus square root, this would be the big one, of b squared, which is negative 870 squared, minus 4a minus 6, and then 183,924. All over 2 times negative 6, which is negative 12. And then we have to go through the process of solving this. So some large calculations, when you simplify all this, you're going to get 870 plus or minus the root of 500, that's 5,171,076. All over negative 12. So in this case, we have plus and minus here, so we have to square root that. Let me give us, if you square root this number, you're going to get 22,074. So x is equal to, 870 plus or minus 2,274 over negative 12. That's going to give you x equal to negative 262 and x equal to 117. We can't use negative 262 because in this case, if we're looking at this, this seems to be a location and time, so x is time in this case. So we can't use this value as negative, we can't have backwards time, but we can have 117. So 117 is a number of seconds. We can use that to determine a location of where this probe will hit the asteroid. We need to do that by substituting this back into the probe's path. So that's y equals 500 times 117 minus 83,024. That's going to give you negative 24,000. Man, 24,524. So on the plane, you are going to have a location of 117 and negative 24,524 of where this probe is going to hit or collide with the asteroid. So while time can be negative, you can have a location, an arc that defines a location, a plane of where this probe will hit. We still have the second probe. We have y equals 500x plus 133,705. So let's check that one out. So same process. Negative 6x squared minus 370x plus 100,900 equal to 500x plus 133,705. Going through the process again, we have negative 6x squared minus 870x from before, and this time we have minus 32,805 equal to 0. We have A, B, and C. Using quadratic formula, we have 870 plus or minus negative 870 squared minus 4 times negative 6 times negative 32,805 all over negative 12. And then as we go through this, we're going to have 870. We're going to simplify this root plus or minus. That's going to give us negative 30,400 420, and here we would just stop. There's a reason why we're going to stop. Is because we can't square root a negative number. It has no solutions in the real sense. So this means this probe will not hit the other asteroid. Or not collide. This probe will not collide. All right. So from this, we can see that sometimes you will have more than one solution in one solution. In the context problem, pay close attention to your x independent value. In this case, time. We have to cross over one of the values. In other cases, you won't have any solutions at all. Now, this was a lot of work to figure out that nothing happens. So we can actually bypass that a little bit. When solving a quadratic linear system, we can leverage the quadratic form to determine how many solutions there are in the system. The root component of the quadratic formula is the key to this method. This is called the discriminant. Now, the discriminant, d equals b squared minus 4ac, has the following properties. This b squared minus 4ac, that comes from this component of the quadratic formula. If d is greater than 0, there's going to be two solutions, as we saw here with a positive number. And if there's one solution, then that means d is equal to 0, because you square root 0, you get 0. And you can't, when you plus and minus 0, it's the same number. One solution in that case. And if d, the discriminant, is less than 0, there are no solutions, as we saw in this case here. So, for example, in this system of quadratic linear system, we want to check if there are any points of intersection. So we go through this, and we have to first get this into standard form to plug into the discriminant formula. So setting f of x equal to g of x, that gives us 2x squared plus 3 equal to 3x plus 1. Moving everything over, we're going to get 2x squared minus 3x, and then plus 2. 0. We have a, b, c. Now our discriminant is b squared, so that gives us negative 3 squared minus 4 times a, which is 2, times c, which is also 2. 3 squared gives us 9 minus 4 times 2 times 2 is 16. That's going to give us negative 7. And since d is less than 0, no solution. So instead of going through the full process, we're able to a little quicker see there's no solution, there's no points of intersection in this particular system. So we're working with quadratic linear equations. You can find points of intersection by some equal to each other, and we can use the discriminant of the quadratic formula to quickly check if there are any solutions, possible solutions in a particular system.